Okay, and let's go to screen share now, uh, so that we can, you can see um, what I'm, okay, what I'm looking at. And okay, here we go. And I believe we ended the lecture last time at this checkpoint that is due today as well. Oh, yeah, while we're discussing this, I'll send you an email about it, but and I think I've mentioned it before, but I really do want you to turn in your labs that you're working on now today and do it sometime before, say, 5 o'clock tonight, or, well, actually, it doesn't matter. As long as you get it in with a calendar date of today, it won't be late. Okay? I'll, I'll won't start grading them until tomorrow morning. Okay, this is where we were. We had done this checkpoint, and now let's, okay, we'll skip down till we get to, okay, now, and you are working on an example in the lab that does show this, that the formula weight of a compound is the sum of the atomic weights of all the elements in it. And we've worked out some examples in percentage composition and so forth. I talked with you yesterday in lab time about nuclide symbols. I'll review it with you here. The nuclide symbol has the symbol for the element. If it's chromium, it's Cr. It has an atomic number that is a lower left subscript to the symbol. And the atomic number is the top number in the cell containing the element on the periodic table. In the example of chromium I just mentioned, it would be a 24. But the atomic number and the symbol are really the same thing. We put it on here for completion and to allow us to do determine the number of neutrons easily. We put the atomic number on the symbol usually, but if you didn't know what it was, you could just look up the symbol on the periodic chart and you could fill that in. Or if you knew what the atomic number was, but weren't given the symbol, you could fill that in. That's the redundant information, really. And the top number is the mass number. And I want to remind you that there's a difference between mass number and atomic mass. The atomic mass of an element is the number that's written at the bottom of each symbol. In the case of chromium, it's 52.00. Now, that's not necessarily the mass number. The mass number is just a count. If you look at almost all of the other elements on the periodic chart, the atomic mass or relative atomic mass is a number with a decimal place, and maybe some of them 4 or 5 decimal places. We can get them that accurately. So the difference is the number that's on the periodic chart is the average of the atomic masses of each of the isotopes of that element weighted by their abundance, and we worked some problems with that. So you've got to remember the number that goes at the top here is not the atomic mass, but it's just a count. It's a count of the number of protons and the number of neutrons in the nucleus. In other words, the mass number is just the total number of particles, whatever they are, inside the nucleus of that element. And we put a superscript charge if the number of electrons is not equal to the atomic number. And many of the elements, for example, most of the elements are metals, when they react, they lose electrons. So generally, say in the case of chromium, one of the very common charges for chromium is +2. That would mean chromium plus 2, with the charge plus 2 here, would have 2 less electrons than it had protons. If it had the same, the charge would be 0. But since it's got 2 less, 20, in this case it would be 22, this would be 24, so you got 22 negative charges and 24 positive charges, gives you a net charge of plus 2. So you can, again, this charge number will be missing. If it's missing, it means the electrons and protons are equal. If it's there and negative, it means you've got more electrons than protons. And if it's positive, you've got more protons than electrons. So this is a shorthand way of designating a symbol for an individual isotope of some element. And that individual isotope could be one of many. We do find that almost all elements have a few isotopes. There are some of them that don't have very many. And I would bet, if I were to look it up, and you can, it's in the CRC handbook, you can look up the isotope masses for the elements there. I would bet you that chromium has probably very minor, if any at all, other isotopes other than the 52 isotope. That would explain why the 52 is a whole number. Another element that's almost isotopically pure is fluorine. Fluorine is element number 9 on the periodic chart, and its atomic mass, relative atomic mass, is exactly 19, or 19.00 anyhow. So I'm betting that that's almost isotopically pure, that of all the fluorine atoms are essentially the 19 isotope. The 19 isotope would be the one that would have 10 neutrons. Its mass number is 19, its atomic number is 9. The difference between this number and this one on the periodic chart is the number of neutrons that's present. So that's a good reason for writing this atomic number on the superscript. It makes it kind of nice to, or subscript, it makes it kind of nice to be able to determine the number of neutrons present in the isotope. So these are very helpful. And I've mentioned these 3 isotopes of hydrogen already. This is the isotopic symbol for the 3 isotopes. This is the hydrogen that you're normally going to find in the laboratory. This one is called heavy hydrogen, and you can make water out of it, and we do, and we have a very useful part of it. In fact, you are going to be using D2O, or heavy water, when you get to organic chemistry, in an instrument called a nuclear magnetic resonance spectrometer. It's used to determine the electronic environment of different atoms and molecules, especially hydrogen in that case. And if you tried to put the compound into ordinary water, the ordinary water would absorb all the signal, and you wouldn't see anything from the compound you had dissolved in the water. But if you dissolve it in D2O, D2O is invisible to NMR. And so you can put samples and dissolve them in D2O and then run them on the mass spectrometer. So you're going to actually use heavy water, and it'll look just like water, except the density would be a little different. It would be, quote, heavy water. Okay, you're not going to deliberately encounter tritium, because it's so radioactive. It would be very dangerous to you. It would be a gas, or even the vapor off of T2O, or the tritium radioactive water, would be just too hazardous to be around. So that one we get exposed to some extent, because it is a natural part of every sample of water, but it's a very, very minor amount, and it's not enough to cause any real hazard in the naturally abundant or naturally occurring water. But there is a little bit there. Okay, now when you build a molecule, the elements are permanently linked together. We call that bonding, and we're going to look in very great detail of how atoms bond to each other. You already know, I guess, from our discussions that hydrogen and oxygen and nitrogen, chlorine, and some of the other elements are diatomic when you find them. When you make hydrogen in the laboratory, you don't make hydrogen atoms, you make H2 molecules. If you collect the oxygen out of the atmosphere or release the oxygen that's dissolved in the sea, that's diatomic gaseous, O2. So most of those elements, hydrogen, nitrogen, oxygen, and chlorine are gaseous at room temperature. Well, chlorine, bromine, and chlorine is a gas at room temperature. It's started to say about the others can be too, but the truth of the matter is, if you took in almost any element on the periodic chart and you boil it, heat it up until it boils, the vapor coming off is almost always a diatomic molecule. There's very few that you can heat to boiling that don't make diatomic molecules. So it's not surprising really that all of the gaseous elements except the noble gases, they don't react with anything. But the other gases are just nitrogen, oxygen, fluorine, and chlorine are the only gaseous elements on the periodic chart as in elemental form. And the helium, neon, argon, krypton, xenon, and radon are gases, but they don't react with each other or with anything else very easily. So most things are diatomic if you put them in the gas phase. And they have atoms linked together. And when we make water, we make H2O. You all know the symbol for it in the formula. It means it's got two hydrogens and one oxygen combined and linked together permanently. And if you've got gaseous water, those molecules are just going to be all together. And each individual oxygen will have its own pair of hydrogens, and they'll always be stuck together. And that's what we mean by a molecule. Molecule contains two or more atoms linked together in a fixed geometry by strong chemical bonds. Now, for example, when we talked about water, water has two hydrogens bound to one oxygen. The angle between of the water molecule is 105 degrees. It can be measured in the laboratory, and we'll discuss how that's done later. So water is a bent molecule, and carbon dioxide, for example, CO2, is a linear molecule. The carbon atom has two oxygens attached to them, but they're exactly opposite each other, and the molecule is linear. Molecular weight of water is 18, the molecular weight of carbon dioxide is 44. But 44 is a gas at room temperature. In fact, you have to cool it, I think, down to minus 68 or something like that before it condenses. And it condenses directly into the solid. At that case, it doesn't go through the liquid phase. It makes a solid CO2 that we call dry ice. And the reason why we call it dry ice is that it looks like ice and it's dry when it doesn't appear to melt. It doesn't form a liquid as it melts. It goes directly into the vapor. That's called sublimation. And water is a liquid, and it's a very unusual liquid because of the shape that it has. And remember, in my very first discussion with you, I told you atoms themselves have a shape. It's the shape around the oxygen atom that causes water to be at an angle of about 105 degrees. And because of that, water is a liquid. And water is a liquid over a incredible range for a molecular weight of 18. I don't know a single other molecule with a molecular weight of anything close to water that is a liquid at room temperature. Water is a liquid at room temperature because life on Earth could not exist. Life anywhere, as we know it, could not exist if water was not a liquid. And so you have to have liquid water to dissolve all the stuff that's inside your cells. And you have to have the water shaped the way it is in order to create a type of association between molecules. It'd be called hydrogen bridging, and we'll talk about that later, or hydrogen bonding. That's responsible for the DNA being in the shape that it's in. So just about everything you can imagine is based or caused by this type of shape of molecules. Okay. So there are some examples I've mentioned to you. Natural gas that you use in Bunsen burners when we're actually able to go to lab is methane, CH4. And if you've got gas heat at home, that's the gas that is supplied to your house. It's methane or CH4. And it has a very precise shape. The angle between all of the carbon atoms, hydrogens on the carbon, this angle I'm tracing out right now, and every one of the others is 109.5 degrees. And the reason for that is because carbon atoms are shaped like that when they bond. That's why that carbon atom is shaped like that when it bonds, because it was shaped like that the moment it was created. And it has that shape and it carries that shape and it's able to do all the things. The stuff that make you up is primarily carbon compounds. Carbons attached to other carbons in extremely long chains, and carbon is the only element that can put more than 3 atoms together and still be stable. I think that's true. No, I know of one other one that puts 4 nitrogen atoms together, but if you hit it with a hammer, it'll explode. And you can pound all you want to on your plastic seat. If you were sitting in the classroom, you could pound on it all you want to and you won't explode. And it's because of the nature of the carbon atom and the shape that it takes. Now, there's a molecular formula for the compound. I can look at methane, for example. I see CH1, 2, 3, 4, CH4. It has a molecular formula and it has a shape. But now there's some elements you could put together and the molecular formula would be made up of little pieces. For example, if we did let's talk about acetylene. You've probably heard of acetylene torches. Acetylene is HC triple bond CH, all in a straight line. So it's C2H2 is its molecular formula. But you can divide that C2H2 by 2 and get CH, and that's what's called the empirical formula. When we get formulas from percentage composition, that's what we're going to be doing a little later. When we determine the formula from the percent composition, what we get is the relative formula, or in the case of acetylene, we've come out with 1 carbon for each hydrogen. And we would not get the correct molecular formula. The correct molecular formula is 2 times that. It'll always be true that the molecular formula is going to be some whole number multiple of the empirical formula. It could be the same. If I took the percentage composition of methane, I would calculate an empirical formula CH4. And it does turn out that that is the molecule. That is the molecular formula as well. You could have twice the empirical formula, or 3 times, or 4 times, or some multiple of it, in getting the molecular formula. Here's one, hydrogen peroxide. You certainly know hydrogen peroxide is different from water. I don't think you want to drink that, and I don't think washing your hair bleaches it. So um, these are certainly different compounds. And hydrogen peroxide, if you want to imagine what it looks like, imagine taking your textbook and you open it to some page, and on one of the pages you put a hydrogen, and then you go down somewhere not quite to the middle at where the page folds, and you would put an oxygen, and then along that fold you put another oxygen, and then open the book up and the other hydrogen would be on the other page. And so it's shaped like that. It's like an open book with one of the hydrogens on one page, one of the other hydrogen on the other page, and the two oxygens in the crease in the middle. And that's what it looks like. But its empirical formula is HO. You see, there's two hydrogens and two oxygens, and its empirical formula is HO or OH. I would write it HO for a reason we'll talk about when we get to nomenclature. And if you got the percentage composition of hydrogen peroxide and determine the formula from that, what you would get is HO. But that isn't the formula of hydrogen peroxide. That's the empirical formula. The formula of hydrogen peroxide is its molecular formula. So the molecular formula is the same one. Now, let's look at some problems, and we're going to illustrate some of the important laws. Silicon and fluorine can form several compounds, and we've got an example. 3 of them that contain only sulfur and fluorine are obtained. If you had a 78.2 gram sample of compound A and decomposed it, you would get 17.14 grams of sulfur, and the rest of it would be fluorine. If you had a 26.4 gram sample of the other compound B, it would have 12.07 grams of sulfur, and the rest of it would be fluorine. And the third one, if you took an 87.9 gram sample of that compound, it would have 26.04 grams of sulfur, and the rest of it would be fluorine. Now, I chose these different amounts because that's probably what you might do in the lab. You just go, you go take a sample, you dump it on the balance, and you see what it weighed. And in one case, it was 78.2 grams of the first compound. And then you take it for analysis and get the amount of materials in each one. So I've tried to make this realistic to what you might do in the laboratory situation as well. Okay, so explain how these data are consistent with Dalton's atomic theory. Well, remember Dalton's atomic theories said that everything was composed of atoms. And that's data certainly consistent with that. Atoms of sulfur should have a different mass than the atoms of fluorine. Dalton's atomic theory said that the atoms of one element were all of the same for that element, but different for different elements. And compounds should have atoms attached to each other, and we would have to decompose that to break them apart, so they had to be attached. Now, they should have different numbers of each atom. We're going to show that in just a moment. And different compounds should be arranged differently. And we can show that, and probably will, I think, in one of the examples. Okay, so all this data is consistent with the ideas of John Dalton when he formulated his atomic theory. Now, let's look at how these data can be used to verify the law of multiple proportions. So remember what the law of multiple proportions said, and you've just worked with a lab with it. It said that if you've got, in this case, 3 compounds that contain only sulfur and oxygen, that if the amount of one of the elements is the same in all of the samples, the amount of the other elements could be divided out into ratios of small whole numbers. So let's make this data consistent and or see if it is consistent, I guess. So if I wanted to have 1 gram of sulfur in the compound, the amount of the fluorine present, the sulfur is, the whole sample weight was 78.2, and we had 17.14 grams of sulfur, so the difference is the weight of the fluorine. Okay, and now if I divide that by 17.14, then the amount of sulfur I'm assuming would be 1 gram. So 1 gram of this, and it's got 17.14 grams of sulfur. Remember, we're doing a conversion. 1 gram of sulfur, 17.14 grams of sulfur to grams of fluorine up here. We do the math, and what we're going to get is 1 gram of sulfur is combined with 3.56 grams of fluorine. Now we do the same calculation for compound B. To get 1 gram of sulfur in it, the sample said we had 12.07 grams of sulfur. So 1 gram of sulfur here, 12.07 grams of sulfur here. This is the grams of fluorine in that sample, it's the difference. When I do the math, I get 1 gram of sulfur is combined with 1.19 grams of fluorine. Compound C, same thing. I want 1 gram of sulfur in the compound, but in the compound, the grams of sulfur was 26.04. So grams of sulfur, it doesn't show the units, but this is grams of sulfur. This is grams of fluorine up here. And when I do the math, I get 1 gram of sulfur is combined with 2.38 grams of fluorine. Okay, now, let's see what the law of multiple proportion says. It says when you have 3 compounds containing only the elements sulfur and fluorine, if the mass of one of the elements is the same in all the samples, the masses of the other element, fluorine, should be in the ratio of small whole numbers. Okay, this is the smallest one, so I would divide everything by it and see what we get. Well, if we divide this into that, we get exactly 3. When we divide this into itself, we get exactly 1. When we divide this into this, we get exactly 2. So the ratio is 3 to 1 to 2 for the fluorine masses in each one of those samples. Okay, so it does verify the law of multiple proportions. Here's your checkpoint on this, and I've given you a similar example with sulfur and fluorine, and now I'm asking you which of these couldn't possibly be a compound of sulfur and fluorine to match the rest of the other 3. Now, unfortunately, you're going to have to try them all 3, I guess. Try all the ratios to see if you get some that work, and you can then tell which one of those is wrong. This will date me for sure because you've never heard of the Bob Newhart show, probably. If you haven't, you might want to Google, go to YouTube and look it up and see if there's not some videos out there. It was a hilarious TV show. I've really enjoyed it. I watched it most every version, every episode. But Bob Newhart is the name. And some of the characters on there, one of them would introduce himself. There was 3 brothers, and one of them would introduce himself as, hey, my name is Daryl, and this is my brother Daryl, and this is my other brother Daryl. So the first version of this, I put it on a test about identifying Daryl, other brother Daryl, and Daryl. and that one people found out about that real quick. Everybody was talking about it, so it's funny. But there's Daryl, and Daryl on here, and then there's an imposter. So figure out who the imposter is.
Dr. Pearson, I have a quick
Yes.
question. For the previous example you just did to get those ratios, did you round at all?
There will be rounding because remember, this is experimental data. And so it's going to be a rounding. And when you calculate a ratio that's maybe, let's say you got a ratio that was 3 to 2, that would be 1.5. Well, when you divide that out in the real data, you might get 1.4999 or 1.5003, something like that. You ought to have a whole number to as many significant figures as your data has. So that's how you know. So if you get something like, for example, if I was expecting 1.5 and I got 1.4629, something like that, I wouldn't round that. I would take that as the imposter, because you have to have the data correct to, if you've got 4 significant figures like we had up there in the weights, we had 4 significant figures, your ratio needs to be a whole number ratio to 4 significant figures for you to say, oh, this is the other brother Daryl.
Can you go over again how you found the ratios? I just got a little lost when you were saying it.
Okay. Now, what I did was I looked at these 3 numbers for the masses of fluorines. You see where I'm pointing? Okay. This is the smallest of the 3. So I'm going to divide everything by that. When I divide this into that, I get a 3. When I divide 1.19 into itself, I get a 1. When I divide 1.19 into 2.38, I get a 2. Again, this would all be correct. I guess I'm only showing 3 significant figures here. So it should be correct to 3 significant figures when you do the division. And I can see this one's exactly 2. I can't tell whether that's 1.5 or not. Let me divide it out and let's just see. If I take 3.56 and I divide that by 2.38, okay, that's an example. When you actually do those divisions, you get 1.495. Now, if I wanted 3 significant figures, that would round to 1.50. So that does give me a ratio of 3 to 2, but it's not exact like this one is. I can see if I divide 1.19 into 2.38, I get exactly a 2 for that conversion ratio. Okay.
Thank you.
Okay. And I told you about that. Okay. This is a good place for us to take about a 10-minute break. And I'll do that. And I will resume recording. And we're here. I need to do a screen share with you. Okay. Now, I've got a note for you right here at the top in big bold, because you're going to have to start learning nomenclature. I'm going to talk to you about it in class, and I may spend some of lab time to reiterate and emphasize and practice naming compounds with you. But you need to start, and there is a file on D2L. I think it's called 31 polyatomic ions to memorize or something like that. It's either got 31 or 32 maybe different ions on that list of things to learn. For example, this compound is sodium sulfate that's shown on your screen. Excuse me. There is also sodium sulfite. Now, and there's sodium thiosulfate and sodium thiosulfite. So there's lots of different polyatomic anions, and you have to memorize those. Now, there is a rationale as to why one of those ions have the ending on the name that they have, like sulfate or sulfite. But there's no way to tell that the ITE or the ATE is SO4 or SO3. There's no way to do that. So what you have to do is just memorize them. And here's what I did, and I think it works really good when you have a lot of stuff to have to memorize. There's just 31 of them, and you'll use them a lot. These are elements that will actually be used in real chemistry labs and maybe in chemical research, or things that you could go to our stockroom at MTSU and pull out to use. So they're the common ones. And with practice, this will come as second nature to you. But until we get to that point, the only thing I can tell you is memorize it. And what I did is I took some little 3x5 note cards. And for example, for the one for this sulfate ion, I would put SO4 2- on one side. On the other side of the card, I would write sulfate. And then what I would do is do this for all of those 31 atoms. I'd have 31 cards in. On one side, I'd have the formula and charge of the ion. On the other side, I'd have the name. And then just what I did, that looked kind of weird, but I'm weird anyhow. I'd be walking across campus and going from class to class. I'd have that set of cards out. I'd pick up the first card and look at it, and it says SO4 2-. And I'd say, oh, sulfite. I'd turn it over and look at it and say, uh-oh, that's wrong. So I put it at the bottom of the stack. And maybe the next time I'd look at the next card, and maybe it was SO3 2-. And okay, I guess sulfite a while ago, and it was wrong, so I'll say sulfite. Okay, I turn it over and look, yep, that's the right one. So I put it in my pocket. And the objective is to get all of the cards in your pocket or in your purse, girls. And then once you get them all in the pocket or purse, you take them back out, turn them over, and run through the process again. And you keep doing that until you get them all in your pocket every time you go through. And then you might try just doing a toss in the air, collect them all together. And so some are showing formulas and some are showing names, and you're just going to run through them all again and see if you can do them in random order, and either from formula or from name. So I wish I had an easier way to tell you to do this, but there's no easier way. We just got to go with it. Okay, so start working on that now. It's going to take some time, and it will be important. I can tell you from exam 1 to exam 4 and the final, you will have nomenclature on that test. And in the beginning, I will give you the name and the formula of the compound. When I get to the end of the course, I will not give you the formula. I will give you only the name of the compound in the question. And if you can't get the formula, you can't even begin to answer the question. So don't just think that, well, I can just blow this off. I don't want to do it. And you're going to cost yourself at least a letter grade or more if you don't learn nomenclature. If you learn it early, you get free points. Those points are going to pile up over the course. And you won't start getting those points until you get this down. So start on this right away. Practice it wherever you go. You don't have to just sit down and spend 6 hours of constant study. That's not a good way to do it anyhow. just do a few minutes at a time, or where you're going from here to there, or whatever you're doing. Just glance at your cards and see if you can get them in your pocket. Okay. All right. Now we're going to determine percent composition from formulas. And the percent of an element, as they told me in third grade, it's the mass of the small element, the smaller mass, divided by the total mass, the big number, and multiplied by 100. So that's the way you get percentage of anything. You want the mass of an element in a sample and the mass of the sample. And a formula of the compound might be a good thing. For example, if I'm looking at sodium sulfate, there's 2 sodiums on it, and I can get the percentage of sodium. So from this, I could say, okay, this compound has 2 moles of sodium. The molar mass on the periodic chart to 1 decimal place is 23. It's got 1 mole of sulfur. That's 32.0. It's got 4 moles of oxygen. Atomic weight of oxygen is 16. If you add them all together, the molar mass of sodium sulfate is 142 grams. Now, the percent sodium is going to be the amount of sodium. And notice I wrote it like this. There's a reason to my madness. I write it like this, and I'm going to enter it into my calculator like this. So if I miss it, I can look at my calculator and say, did I remember to put that subscript 2 in that formula? That's a common mistake. So I can check for that. If I just write 2 times 23 is 46 and put 46 up there, I'm going to look back later if I made a mistake, and I don't have a clue where 46 comes from. It's not any of the atomic weights on the chart. So it's best to do it this way. And then I'm going to multiply it out and divide. So I get 32.4% if I take 2 times 23 and divide by 142. Notice the grams cancel, the unit is percent. Okay, now if I'm doing sulfur, it's the same way. It's the mass of the element, 1 times 32 divided by the total times 100. It comes out to be 22.5%. The amount of oxygen, percent, is 4 times 16 grams of oxygen. Total mass 142, 45.1. Now, I did that deliberately like this because if you add them together, it should be 100%. And so if I had just taken these 2 numbers and subtracted from 100 to get this number, if I had missed either one of these, I'd miss this one too. And so don't do that. Calculate the percentage of everything in the formula and then see if they add to be 100%. This would generally give you a check on whether you did the math correctly or not. Now here's another one, aluminum sulfate. So it's got 2 moles of aluminum. It's 26.98. I've added another significant figure. It's 3 sulfurs. Now remember, if you've got a parenthesis like I'm showing, circling right now, you've got that parenthesis and the number out here, that multiplies everything inside. So 3 times 1 is 3 sulfurs, and the atomic weight for sulfur is 32.06. And then oxygen is 3 times 4 is 12. I've got 12 of those. The atomic weight of oxygen is 16. When I add all these up, I get 342.14. And let me tell you again, I'm going to enter this number in the calculator, 2 times 26.98. But I'm not going to type in 342.14 because that's still on the screen of my calculator. What I'm going to do is I'm going to take 2 times this, divide by answer. The answer is stored on your calculator. It's on almost all the calculators. It's on the very bottom row, the second key from the right. It's a second function over that little change the sign key. And so if I do divided by second function answer, then I'll get the percentage of this one. And I didn't have to enter that number and run the risk of me writing 324.14 instead of 342.14 or 432. I do crazy stuff, I told you. So I try to avoid that every time I can. And also it's quicker. I can push second answer, that's 2 keystrokes. If I wanted to do this one, I have to do 1, 2, 3, 4, 5, 6 keystrokes in order to enter that number. And remember, I'm trying to teach you how to do things quickly. Don't waste time that you don't have to use that way. Every minute you save is going to give you a minute more to work on the things you don't know so well and you're having difficulty with. So don't waste time on the things that you can do quicker. Okay, and here's the percentage for the others, and we add them all up, we get 100%. Okay, this is a funny compound that I found in a textbook one time, so I just thought, hey, let's do one with that one. It's uranium, oxygen, tellurium, and fluorine are all together as this part, and they are attached to, there's 6 of them attached to the oxygen atom, or uranium atom, and this is the formula for the compound. So again, we can unravel the formula. You've got 1 uranium, you've got 6 times 1 oxygen, 6. You've got 6 times Te, 6 of them, and you've got 5 times 6 is 30 fluorines. And the atomic weight of uranium is 238.03. The atomic weight of oxygen is 16. Tellurium, if you can find it on the chart, is 127.6. And 30 times fluorine is this. It's a big molar mass, 1669.63, but we don't care what the numbers are. It doesn't matter. It's all the same thing. You take the little number, divide by the big number, multiply by 100. That's what they told me to do in 3rd grade. And we get the other numbers the same way. And then if you add them all up, they should add to be 100, and they will. So the concept is simple, but we took some time to unravel formulas because you have to be able to do that. And if you make a mistake here, you're going to get the wrong percentages, and guess what? It is going to add to 100. So be really, really careful that you interpret this part right. Okay. All right, here's your checkpoint on that. And you're to calculate the molar mass of this compound. And by the way, this thing does exist. I think it's called Prussian blue. It's a really intense blue dye that you can make containing iron in the left side of the formula. We're going to call that the cation part. And it contains iron also in the anion part. And you have to total up both of those ions in order to calculate the percent composition. So, and that may not be the one that's on D2L. Check it carefully. And when you submit a checkpoint, be sure you submit the one that's on D2L, not the one that's on the PowerPoint, because I've changed almost all of them for this summer. Okay.
I'm sorry to interrupt. I don't know if it was only myself, but when I printed out checkpoint 4, it doesn't have a problem on it. It just says your problem for 3 points. And then it talks about answers below and percentage of Fe, percentage of C, and percentage of N, but it doesn't give like a compound.
Oh, it doesn't give the compound?
No.
Oh, okay. I guess I better fix that then. I could let you make one up and do it, but let's give you one. So this one was segment 2. That would be checkpoint 3. Is that the right?
I think it's checkpoint 4.
Checkpoint 4.
Thank you.
All right, very good. I've made myself a note. I'll get on that after the lecture's over. Okay. Now, I mentioned before that when we're writing formulas, there is a left side of the name and a right side of the name, a left side of the formula, a right side of the formula. The left side of the formula is generally for most of the compounds we're dealing with right now, they're what's called ionic compounds, which means there is a positive ion and a negative ion that make up the formula for the compound. So atoms or species that are charged are called ions. The cations carry a positive charge, and the anions carry a negative charge. And as we talked about when we did nuclide symbols, it tells you whether you got more protons or electrons, which one's most, inside the formula of that species. And ionic bonding is nothing but electrostatic attraction between cations and anions. Excuse me. The positive ions will attract each other at all distances, but generally as they get closer, the force of attraction gets higher, and it really generally goes as the square of the distance. So if you if you move two ions from here to there, and there was twice as far as from here, then it would be 4 times the attraction when you brought them in closer to each other. So that's not terribly critical, but I wanted you to see that if you started two atoms off at infinity, okay, they're going to start heading toward each other slowly and slowly and slowly. But as time goes by, the force increases and they get faster and faster and faster. So that they're going to come together and stick together and form an electrostatic attraction between the positive and negative ions that gives you rise to what's holding those pieces together. Now, very often, an element will gain or lose electrons, become positive ions or negative ions, depending on where they are on the periodic table. Let me put the periodic table back up for you. And so, okay. Now, if you look at the periodic table, you might not see the individual values, but you can see the form. This little stair-step line that's going across here separates the metals that are on this side of that stair-step from the non-metals that are on this side. Now, the non-metals there's many, many more metals than non-metals. And the important thing about that is the metals, when they tend to react, they tend to lose electrons. For example, when sodium reacts, it always loses 1 electron in forming a formula for the compound. So sodium always becomes +1. That's true for everything in this family. The reason for that is this column over here, called the noble gases, group 8. They don't react with hardly anything, which means, I'm so sorry, I got a little bit of hoarseness this morning. That means that these elements are happy with the way their electrons are arranged. So all elements would like to get a number of electrons like the noble gas. So metals tend to lose however many electrons it needs to get a number of electrons like one of the noble gases. If I had sodium, sodium is element number 11, and it could lose 1 electron and become like number 10, and that would be neon. So all of the elements will do that. If I started over here with calcium, I'd need to lose 2 electrons to get back. So all of this family is +2. That's what you're going to generally find for the whole periodic table. The table I give you have these columns labeled 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Or maybe this column is or labeled in some cases. But that's the number, that is the most likely positive charge. So if that element is behaving like a metal, it's going to come in the first part of the formula for the compound. It's going to be named first. We'll talk about the way they're named in a moment. And the nonmetals, the ones that's on this side, tend to gain electrons. So fluorine, for example, really gains electrons readily. It's element number 9, so it needs one more. So it would have 10 in its compound, just like neon does. And so all of the elements in group 7 gain one electron if they're nonmetals, and they're going to appear on the right-hand side of the formula. And so if I look at oxygen's family, it's group 6. It would need 2 more to go to 8, so it would form a -2 ion. And group 5 would need 3, and 6 would, and so forth. 4 would be 4, and so forth. So the negative charges are generally the group number -8. So the group number is 7, 7 minus 8 is -1. For oxygen, the group number is 6. 8 minus 6 is -2. And for me, it's just easier to start at this 7A column and say -1, -2, -3, -4, -5, and so forth. So any of the elements has both a positive charge that's possible and a negative charge that's possible. The metals are most always going to take the positive charge. The nonmetals are almost always going to take their negative charge to get the formula of the compound. Okay, so metals tend to lose electrons, become cations. Nonmetals tend to gain electrons, become anions. And now you know how to look at the periodic chart and tell whether an element is a metal or a nonmetal. Now, this summarizes what I just told you and pointed out to you. The representative elements are a group of elements on the periodic chart. They're generally the first 2 columns on the left and the last 6 columns on the right. Those are called representative elements. And they tend to have a charge equal to their group number. Or if it's a cation, if it's an anion, a nonmetal, then it has the 8 minus the group number for those. So the representative nonmetals, those would be, now again, that's in group columns 1A and 2A, and 3A, 4A, 5A, and 6A. The representative elements, that little A by their column heading, is telling you they are what we call representative elements. And we'll talk about why that name a little later. The middle in between, it goes between metals and nonmetals. They're called transition metals. They are metals, but they're on the transition from the metal side to the non-metal side. They bridge the gap in between those. Now, they can also all have a +2 charge, but they can have a very prominent second charge, and that is the group number. And on our periodic charts, these are all labeled B. So, and if you look at the columns on the periodic chart, I don't want to break our discussion to go to the chart. You should have one there to look at. The first column on the left of the transition series is labeled 3B and 4B. Now, the reason for the 3B and 4B and so forth is if I started at scandium, element number 21, I would need to go back 1, 2, 3 to get to an element that's a noble gas. It's argon. So it's called 3 in the non-transition element, non-representative elements, the transition elements, is called 3B. The next column, titanium, and its elements would need to do 4 to get back, and then 5 and 6 and 7 when you get to manganese. Now, iron, cobalt, and nickel, notice they're labeled 8B. All 3 of those columns is 8B. That doesn't mean they have 8 electrons that they're going to lose or gain. Generally, that group in the middle is going to be +2 or +3. And, sometimes I write those in Roman numerals, and I can remember that then, because 8 in Roman numerals is VIII. So if you ignore the V, it's 3. So, I have all kinds of quirky things that I use to memorize stuff. So that 9 elements in group 8B are +2 or +3. And then you go all the way over to the end and you get copper now is +1 and zinc is +2. Copper family is 1B and zinc family is 2B. And their charge is going to be either +2 or their group number. Again, you expect copper to be either a +2 or a +1 because it's in group 1B. You expect zinc, for example, to be +2 or +2. +2 because all the transition metals can be +2, and +2 because it's in group 2B. Zinc never forms anything except a +2 ion, and cadmium never does. Mercury sneaks it does something that we didn't expect. It does form a +2 ion, but it does form an Hg +2. But it also forms an Hg2 +2, a diatomic cation that has 2 mercury atoms. The charge, sum of the charge of both of them is +2, so each one of them is +1. So mercury can form 2 different kinds of compounds. One that has this diatomic cation, Hg2 +2, and one that just has the monatomic cation, Hg +2. Now, Hg2 +2 is one of the ions that's on your 31 polyatomic ions to memorize. Okay. Now, the rare earth elements, the elements across the bottom, I've told you that these 2 rows at the bottom of the periodic chart actually go in between group 3B and 4B. Well, these are called rare earth elements. Sometimes they're called inner transition elements to indicate that they are inside the transition metals. They go inside between, for example, cerium through lutetium goes between lanthanum and hafnium. And thorium through lawrencium goes between actinium and rutherfordonium. Crazy names. Almost as bad as the ones I came up with. All right, so there's 30 or 31 polyatomic ions to memorize. I think it's actually 31. And you have to memorize those. Now, when metals react with nonmetals, they form an ionic compound. And they're held together by electrostatic forces. And that's what we mean by ionic bonding. Nonmetals also stick together sometimes to form covalent compounds. Like, for example, CO, carbon and oxygen can make CO, or they can make CO2. It's not an ionic, but it's not an ion. But if you looked at CO2, it would have sort of a formula you'd predict. For example, if you thought carbon was +4, which it could be from its position on the chart, and oxygen's -2, it would take 2 oxygens to combine with carbon to make carbon dioxide. That gives the correct formula, but it doesn't give the correct properties. Carbon dioxide, if it were ionic, would be a hard crystalline solid with a very high melting point. Instead, it's a gas at room temperature, and life depends on that being a gas as well. It's a gas that has to be in the atmosphere for plants to use. For example, that great big oak tree that's out in your backyard somewhere or out in the forest that you've been in somewhere. That great big oak tree, if I were to ask you, where does the mass of that wood come from? Most of you would guess wrong. You'd think it comes from the soil, from the dirt, from the water, the things dissolved in the soil. No, it needs those things to live, but the mass of that tree came from carbon dioxide in the atmosphere. Trees have the remarkable ability, and plants have the remarkable ability to be able to extract a compound, carbon dioxide, from air when the air only has 300 parts per million, maybe 400 now, of carbon dioxide in it. The carbon dioxide is plant food. There's a reason for it being there, and it's important that it be there. Okay. So when you're building compounds, you've got to take a number of the cations and a number of the anions to put together so that the net charge is 0. So you've got to have the same amount of both positive and negative charge. So let me show you the way you ought to think about this. Now, we couldn't actually do this experiment. Suppose I could put aluminum ions, they're all +3, into a beaker. And I could put oxygen ions into a separate beaker. Okay, so I'm going to make a stack of oxygen ions over here. Let's back it up. Now, actually, if you could do that, just count the number of charges that's in there. And if you could put that many charges in a beaker that wasn't balanced and put the balancing charge in the other beaker, you could set them across the bench from each other and a spark would jump. So it's not going to happen. We can't do the experiment, but we can visualize doing it. I can imagine I'm able to get individual aluminum ions and individual oxygen ions to build a compound of aluminum and oxygen. I would take one of each, and now I check my charges, it's not neutral. I've got too much positive charge. So I'd go get another negative charge and put it in. Now I'm looking at this, I've got -4 with +3, I've got too much negative charge. I need to get another positive ion to go with that. Now I've got +6 and -2. I've got too much positive charge again. I need another negative charge. When I do that, I've got +6 and -6. That now is the formula for aluminum oxide. It's Al2O123, O3, Al2O3. Now, I want you to be very careful, because if I had, for example, an ion over here that was 4, and an ion over here that was 2, I could take, one of the 4 ions and 2 of the other ions, and I could get a neutral compound like that. But what if I had +2 and +2? I could possibly put these together as 1 of each, or 2 of each, or 3 of each, and so forth. Now, the formula for the compound is, and this one was Al2O3, and you can get it for that particular case, like the book shows you, of just transposing from the charge number on one becomes the subscript of the other. You can do that on this case. But if you had a +4 and a -2, you would write a formula SN2O4. That's not the formula for tin-4 oxide. It's SNO2. So if you crisscross charges, you better check to be sure you can't divide something out of all of the subscripts in the formula. You'll get it wrong if you didn't do that. Now, we're beginning nomenclature. So let's think about naming compounds. There is a system to the way you name compounds. The name has two parts. It has a left part, a beginning part, and a right part or ending part. The left part is the one that's more metallic, comes to the left. So again, remember where they are on the periodic chart? You go down that zigzag line. The further you are away from that zigzag line, the more metallic an element is. So if I'm looking at an individual column, the most metallic element is in the bottom of the column, and every place on the periodic chart. And if I'm looking left to right on the periodic chart across the period, the nonmetals are on the right and the metals are on the left. So the element that's furthest to the left is the most metallic of the bunch. And so you name the compounds by putting the most metallic elements first on the left. And they're generally cations, and they're named just like the metal. So if I've got sodium chloride, the name, you know, sodium chloride is for NaCl. So the cation is named just like the metal, and the anion is named just with the non-metal part, but it's been changed. I don't say sodium chlorine as the formula, as the name of sodium chloride. So the right-hand side name has been changed, but the left-hand side is the same as the metal. Now that has some unfortunate consequences. I'm thinking about eating breakfast again. Suppose you're having cereal. You can look at the box of the cereal and it gives you the composition. It'll tell you how many milligrams of sodium it has in a serving. I tell you, it don't have any sodium at all in there. If it had sodium in there, it'd be catching on fire. You pour milk on it, it's going to burn. So it don't have sodium in it at all. It has sodium ion in it. And they're not the same thing, although they're named the same and sometimes implied that you got sodium in your cereal. You do not. You have sodium, probably sodium chloride is what they put in salt to make it taste better and do stuff like that. So it's probably put in, or it might have a little bit of sodium in the grain or whatever that the cereal is made from. Now, let me really rock your boat. Look on the cereal, and maybe you're picking one that's high in iron because you think you need a lot of iron in your diet. Guess what? If it says you've got 50 milligrams of iron in a serving, you've got 50 milligrams of iron in there. They actually do put iron in your cereal to fortify it for iron content for people who want to pick up iron. If you don't believe that, here's a simple experiment you can do. Take some of your cereal, pour water on it, and get it really, really soggy and mushy, and crush up all the pieces and stir it and soak it until it's just a mush, and then throw it in a blender maybe, and just beat the tar out of it. And then go get a magnet and drop it in that soup and pull it back out. You'll see the iron that was in your cylinder, your cereal. That might be a good experiment to try to show people. It's kind of fun. Pick something that's got a lot of iron in it. Okay, all right. So the cation part is named by the metal. So anything that's got sodium as the first part of the name, it's just going to be called sodium something. So it's named sodium in all of its compounds. Now, all the metals except these: group 1, group 2, zinc, cadmium, aluminum, and silver. All other metals except these have multiple charges. So you have to distinguish between, for example, iron, whether it's +2 iron or +3 iron. It could be either one of the two. The way you distinguish is use a Roman numeral to signify the charge of the ion, not the number of things attached to it, but the charge of the ion. So we're going to use a Roman numeral. Now, iron +3 is written as iron with a Roman numeral 3, and is pronounced iron 3. So if I've got FeCl3, it's called iron 3 chloride because the iron has a +3, not because it's got 3 chlorines attached. Not because it's got 3 chlorines attached. It's called iron 3 because the iron is in its +3 charge. That's important. And iron +2 would be called iron 2, and it's pronounced iron 2 chloride. So FeCl2 would be iron 2 chloride. Let me illustrate it. Sulfate is SO4 2 minus. If I had FeSO4, that would be iron 2 sulfate, but it just had one sulfate attached. Remember, the Roman numeral refers to the charge, not the number of things attached to it. It's a very common mistake. Anions keep the name of the element, but you just keep the stem part. Like you almost think of an example. NaCl, everybody in the world knows that's sodium chloride. Okay? How did you name it? Sodium, the name of the first element. How do you name the second? Chloride. Well, the chlor tells you it's sodium chloride, not sodium bromide or iodide or nitride or oxide. It tells you the element, you keep enough of the name, the stem part, and you change it to IDE if it is a 2-element compound. So you can have iron 2 chloride, you can have iron 3 chloride, or you could have sodium bromide or sodium iodide. And from the name, you would know what elements are involved. And from this ending, it's telling you that that element is its negative charge, and it is one of 2 elements in the compound. Now, there's one exception to this. Let me get back and show you. Actually, there's 2 exceptions. They're all on your polyatomic ion sheet, so it doesn't matter. But Cn minus is called cyanide. So NaCN would be called sodium cyanide. Now, the name sounds like it's a 2-element compound, but it's not. It's because the anion is this one, and in these kinds of compounds, we just name the cation and anion, sodium cyanide. So there's an element like, there's a polyatomic ion. There's this one, is also a polyatomic ion, but it's called hydroxide. Yeah, the name makes it sound like it's 2 elements, and the second one is hydrox. It's not. That's the name of this compound, this ion. So if I put that with sodium, NaOH, I'm going to have to recognize that that OH is a polyatomic anion, and I'm going to call it sodium hydroxide or sodium cyanide. So the IDE ending on those, there is a reason for that, and the reason is that those compounds actually behave. Behave the way the chlorides, what we call halides of group 7. They will form all the same compounds. Cyanide and hydroxide will form all the same compounds with the same kind of formula that chlorine would. Okay, so that's the reason why when they named those polyatomic ions, they were sometimes called pseudo halogens. Group 7 is a halogen column. So they behave like halogens, and they have the ending IDE just like chlorine would, or bromine or iodine. Okay? Now, so you keep the chlor, gives you the stem name, and you go to IDE. Now, the polyatomic anions keep the same name, and you have to memorize them. There's no way you can figure out the name of MnO4 minus is permanganate. There is an explanation, there's a reason for it, but you can't take that formula and generate that name. And you can't really take that name and generate that formula. You have to memorize them. But once you've memorized them, naming these things is duck soup. Look, if you wanted sodium permanganate, you'd put Na with MnO4, and they're both sodium plus 1. MnO4 is minus 1, so Na MnO4 would be sodium permanganate. Be easy to do if you've memorized that name. If I've got calcium, calcium is plus 2. So it would take 2 of these. So the formula for calcium permanganate would be Ca with a parenthesis, MnO4, and a little subscript 2 to do that. So naming compounds with involving the polyatomic ions is really, really easy. If you've memorized the name, it's really, really, really impossible if you haven't. I hope I'm making the point. Now, you're going to name other compounds that are not made of well, you're going to name cation, anion in that order. I forgot that we did this here. Okay. So you're going to write them with the sodium first, and like 10. Now, here's an example I told you a while ago. SNO4, SO4 is negative 2. There's 2 of them, so 10 is plus 4. So this is 10,4 sulfate, not 10 disulfate. I will count that wrong every day of the week. You don't use those prefixes except in a special case I'm going to show you in a moment. This compound is 10,4 sulfate. And it's 4 because the 10 is plus 4 in that compound. Now, we can name these as binary acids. Typically, for example, there is such a thing as hydrogen chloride, HCl. It's a gas. But most of the time, you will not encounter that deliberately. I mean, if you take 16 molar hydrochloric acid and smell of it too closely, you'll understand why you don't want to smell that stuff. It's a very toxic, very caustic gas that would destroy your lung. So you're going to handle that stuff, even the aqueous solution. But if I told you HCl is in the lab and you wanted to go get a bottle of it, you'd get a bottle that said hydrochloric acid on it. You all know that name, don't you? Okay, so when you're naming binary acids, that is an acid that has a hydrogen in front and an anion ending in IDE, then you name it this way: hydrostemic acid. So it's going to have a hydro in the name. If it's HCl, you know that's hydrochloric acid. That's the way you name the compound. H2S. This is sulfide. It's a 2-element compound. So it's going to be named what? Hydrosulfuric acid. All right? Not sulfuric acid. We know what that is, H2SO4. I'll show you about the naming of it in a moment. But any anion, to use this type of nomenclature, if you're going to put a hydro in the name of the compound, it absolutely must have only hydrogen connected with only an anion with IDE. Then you can name it that way. Okay. The other acids are with the polyatomic anions. And if you've got ATE in the name of the polyatomic anion, that'll be the ending of the name of the polyatomic anion. When you make an acid from it, you change the ATE on the ending to IC and then add the word acid. If it's ITE, you change that ITE to OUS and add the word acid, and that gives you the name of the compound. So naming again is going to be easy. All 31 of those polyatomic ions either end in ATE or ITE. If they end in ATE, the acid is going to be the ic acid. If they are ending in ITE, the naming is going to be the us acid. Never, 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 never use hydro in the name of those kind of compounds. Don't ever call a H with a polyatomic anion as hydro something acid. That's going to be response B on the test, and it will be wrong. Guaranteed. Okay. All right, how do we name this? That's sulfate. Okay, so this would be ATE goes sulfuric acid. Now we had to put the UR because sulfic acid wouldn't identify sulfur. So sulfate is okay, but when you want the acid, you can't call it sulfic acid. You call it sulfuric acid. You're changing the ATE to IC in that case. It's very uncommon that you have to do something to that. Okay, HNO2. Well, what would that anion be? NO2 minus is called nitrite ion. So you change the ITE to OUS, and it's called nitrous acid. What's this? If you memorize the polyatomic ion, you'd recognize ClO3 minus is chlorate ion. So how you make the acid? Just change the ATE to IC. So it's chloric acid. So this is chloric acid. HCl, without the oxygens, HCl is hydrochloric acid. See the difference? You recognize HCl as a binary acid and name it with the hydro. You recognize this polyatomic anion as an acid of a polyatomic anion. You don't use hydro in its name. Instead, you just take the anion name that you've memorized, strike out the ATE, and put IC in its place. Now, what's this called? OCl minus is one of the polyatomic anions. It's called hypochlorite. How are you going to make the acid? Real easy. Just change ITE to OUS, and you've got the acid. So you see, if you memorize these anions, if you memorize that as hypochlorite, you know this acid is hypochlorous acid. The only thing you're changing is the ITE to OUS. Now, suppose you had nonmetals. We mentioned CO2 a while ago. We call it carbon dioxide. You know that. So we're still going to name it with the more metallic element name first. Carbon comes to the left of oxygen, so we're going to write CO2, not O2C. CO2. Metal first, non-metal second. Now, some places in the world do that differently. So if you transferred here from another country, you may have named it the other way. But guess what? You're not in your home country anymore. You're in America now. So you have to go by these rules. Don't try the European rule for driving. You'll get in a wreck before you get 10 miles from your home. Or you'll be arrested and taken to jail for drunk driving if you drive on the wrong side of the road. Okay, you use prefixes to signify the number of atoms that are present. Okay, if you've got 2, that's di. If you've got 3, that's tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. And we don't often have subscripts greater than 10. So generally, you're going to be able to name almost everything with just being able to count to 10. in whatever that is, Greek or whatever. So you got to count di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You ask, well, where's mono? Nobody wants mono. All right. You do use it in some cases when you have to. For example, when we wrote CO2, you didn't say monocarbon dioxide. You didn't say that, because that if you just said carbon dioxide, you implied there was one carbon. You didn't need to say specifically one carbon. If you want something other than one, you would say, like in oxygen, you don't say carbon oxide or carbon for CO2, you're going to say carbon dioxide. But if you had CO, you would have to say carbon monoxide. And that's a case where you do have to use the mono. But whenever you've got mono with oxygen, you don't want to put the two O's together. So instead of saying carbon monoxide, we just say carbon monoxide, so that it sounds better, I guess. I don't know. Okay, so the first element is named as the element, carbon, and the second element uses the stem part and the IDE in the naming. So you can have carbon monoxide or carbon dioxide, or you could have nitrogen trichloride, could be a compound, or dinitrogen or diphosphorus pentachloride, stinky, awful, terrible, nasty compound that you sometimes have to use in organic chemistry. But all of those are going to have the IDE ending then. So they're going to have prefixes, and you use the prefixes when? Only between nonmetals. Don't you ever tell me FeCl3 is iron iron trichloride. I'll count it wrong. But if you Google it, you'll find it. So be careful. The internet is a wonderful resource, but I can guarantee you everything you read on there is not correct. A lot of it is, but a lot of it's not. So that's part of being educated, is to be able to look at something from some sources you've not seen before and decide whether it makes sense or not. And if it don't make sense, then don't go around quoting it. You check it out until it does make sense, or you can say, they got that wrong. Okay, that'll happen. All right, so here's some compounds of all of these different elements and ions, and it's asking you to name all of these and predict the formula of the compounds and the charges of the elements you expect. And for example, rubidium's in group 1, it's only going to be a +1. Barium's in group 2, it's only going to have a +2. Titanium is in group 4B, so it's going to have a 4, but it's also going to have a 2 because it's a transition metal. Nickel is a transition metal, so it's going to have a +2, but it's also going to have a +3. It's in the group 8 bunch. Zinc is only going to be +2. Silver is only going to be +1. Aluminum is only going to be +3. Selenium is in group 4, so it's going to be either it's in group 6, I'm sorry. It's going to be either a +6 or a -2. And iodine is either going to be a -1 or a +7. Now, these anions, we expect this charge. We don't expect them to be in a cation. But for example, ClF7 does exist. IF7 really is easy to make. And so it is possible to have these other charges, but these are the only charges you would predict for any one of those. And of course, you can see the charge on carbonates -2, and this would be called hydrogen sulfide, or it's also called bisulfide. Bi is often used for hydrogen when it's connected to something that would make it acidic, like H with some nonmetal. So you can call it this hydrogen sulfide, or you could call it bisulfide. And this is ClO2 minus this chlorite. All right, so I'm just gonna click through these. These you can all do. We're out of time anyhow. So you need to practice all of this. I could do it all day. And to me, it just comes natural because I've done it for, oh gosh, ever since high school. That's been eons ago for me. So you can name all of these compounds. This will give you practice. You can check yourself, see if you got it right, and do stuff like that. And do practice this. The only way to learn it is to do it. Okay. All right. I'm going to stop the recording here.